if you are free to join, if you could just turn on your webcam, and then we'll just spotlight you. So it'll just take us a moment. So if anyone's still around, and then we can follow up this discussion all together. So we'll just give us 1 second while we just bring everyone back. Hopefully we have everyone at Spotlight. Spotlight. Brilliant. At Spotlight. At Spotlight. Excellent. Fantastic. We've got so many people that have stayed around. That's fantastic. Excellent. So I'm sure, apologies if I've missed you. Please do switch on your webcam, and Veronica and others can help Spotlight. Excellent. So thank you all for the talks and for joining us throughout the day. I'd be really interested to get again some of your thoughts, having seen the other speakers, getting your thoughts. But maybe one question I had was, we've had quite a large focus today on the kind of the evolutionary side. And maybe just as kind of a slightly controversial point for in terms of advancing intelligence, advancing embodied intelligence, how do we bring all this evolutionary knowledge forwards into our robots, into designing and developing systems that exploit embodied intelligence? Just as a starting point, but in general, to get everyone's reflections on the kind of topics from today. Would anybody be willing to start us off?
Josie.
Thanks, Thrish. Please.
Emily, go for it.
I'm happy to have a go.
Ah, John, perfect. Thank you.
Well, I would start by answering with my standard answer that diversity enables discovery, which is a phrase I learned from a professor in grad school. I think it applies in many different ways. And evolution is all about diversity. So there's a huge wealth of organisms to draw from in learning about anything you want to apply. So I think that's part of the answer, but there's more to it than that is more specific.
Thank you. Emily, did you have anything to?
Yeah, I would agree with John, actually, that it's looking at animals, and I was I'm always joyful to see animal examples coming into robotics design, because millions of years allows things to get figured out, and they're really interesting. And so yeah, observing and factoring that into design is really, I think, going to be powerful.
Yeah, Nikki, please.
Yeah, well, I think one thing, thinking about different evolutionary mechanisms could be quite helpful here as well, because if we think within the biological systems, so the animals, we know that there are basically two kinds of ways, maybe more, but the simplest is two kinds. When you think about the evolution of intelligence, you either think of homologous evolution in closely related animals, or you think of convergent evolution in very distantly related animals. And in addition to that, you could also have the possibility of having evolution that results in diverse kinds of intelligence with different selection pressures. So I think that's quite an interesting thing to factor in. So, for example, within work on comparative cognition in animals, you see that members of the crow family and probably members of the parrot family and other examples show similar cognitive abilities to those of certain large-brained, long-lived, highly social mammals, such as the chimpanzees and the dolphins and the elephants. And the idea there is that it's probably similar selection pressures, longevity, highly social, very good at keeping track of certain aspects of the physical world, such as the ability to use tools and to track time when things ripen and when things go bad. But of course, in things like the cephalopods, the octopus and the cuttlefish and the squid that we were talking about earlier in various talks, actually, including my own, obviously they're not long-lived, they're really quite short-lived, and most of them are not highly social, at least not in the way we think of sociality when we talk about it in birds and mammals. They may well be keeping track of other individuals of different species that are their predators. They may also be thinking about individuals within their own species, which may be sexual predators, but it's not in terms of alliances and affiliations in the way it's described when you talk to people that study birds and mammals, suggesting that there's probably different predation pressures. Indeed, loss of a shell and therefore being vulnerable as living lunch or dinner is one of the problems that they have to deal with, if you like. So I wonder whether thinking about selection pressures is also quite interesting in terms of artificial intelligence evolution. Comes back to the idea of embodiment, that, different kinds of machines might have different kinds of pressures on them in order to solve these problems, albeit ones that have been programmed by incredibly talented people that know all this stuff about robotics, computing and engineering, stuff I don't know. So apologies in advance for my ignorance, but I just thought that might be a point worth considering. You've probably considered it already. It's just a thought from a biologist.
Interesting. So are you thinking more about kind of evolutionary algorithms as ways of using that for design, or looking at how do selection pressures or drive the direction of AI and kind of robotic technologies?
I think both could be interesting. I mean, we know that in the animal world, Darwin's finches would be a good example of looking at how environments shape adaptation and what that can do in certain circumstances. And many of your talks today have touched on that, but I could also see it being in terms of what selection pressures would shape the development of AI.
No, I get. Oh, sorry, Thrish, please.
Coming from a robotics background and thinking about these ghost circuits, I feel that it is a massively parallel attempt to optimize the efficiency of ghost circuits, right? So like no animal or any tree or anything can be separated from another. They are in this, they survive in this community, right? So in the orchestra. So it is like, if you think about it as a symphony, this orchestration of ghost circuits and then their behavioral outcomes are what matters, right? So it is not the kinematics or the flesh or bones that matter, the behavioral outcomes as a collective that matters. So everybody is trying to parallelly optimize their gain, and then they, because this is a massively parallel attempt and multi-parameter optimization process, there can be local optima, right? So like there's this massively redundant system. There's no one single solution. And then diversity is a natural outcome of that kind of a process, right? So it is inevitable that diversity emerges out of a very nonlinear landscape of optimization. So that's how I see it.
That's really, to add to that a little bit, one of the things that I find both like great about optimizing in engineering context is that you can optimize for things. You can say, okay, energy, let's do energy, let's do speed.
Yeah.
Whereas in biology, from an evolutionary perspective, you're optimizing for a landscape of ever shifting things. And so it's really hard to say, well, this animal does this way because they're optimized for X.
Yeah.
Because there's constant competing design needs in any one organism. So yeah, that's interesting. I really like your ghost circuits idea, because it so captures that ethereal part of successful performance, which is just it lined up.
Yeah, and then a single animal can be part of multiple ghost circuits depending on the time, right? So like it can be predatory behavior, survival behavior, food seeking, mating. So depending on what they do, right? So they recruit different ghost circuits, and then they try to optimize everything, and then naturally diversity emerges out of that, right?
Yeah. and possibly, you know, Olympic performance as well. Like the difference between an amateur doing something and Olympian doing the same thing is that they've really fine-tuned their ghost circuits.
Yeah, exactly.
Which is very cool.
Yeah. And then one building block in that ghost circuit changes, it propagates across everything. So that's the beauty of the connectedness of a ghost circuit.
It's lovely. I really like that. Thank you for sharing it.
Yeah, thank you.
One thing I wanted to maybe also follow up about is it's interesting now you're talking how it's like the function and the output behavior that maybe matters more than what is the underlying mechanism that causes it. And I think we saw a lot of different tests for that. So, for example, Nikki, you had magic tricks as kind of a benchmark or a mechanism for can the being or the human, either way, or the robot understand maybe intelligence behind it. And also Jonas as well, I think you also had something about kind of human-robot interaction. And is there some estimation, or can the human predict or think there'll be some intelligence? I'm just wondering for all of you, what is your perspective on how we could benchmark or analyze or define does something have this kind of emergent embodied intelligence? What is all your different viewpoints on kind of what would be your benchmark, what would be your test for your different robots, for your different animal studies of what has this intelligence, or what do you think we need from an embodied intelligence system?
Josie, I kind of slightly I am skeptical about this intelligence thing. Intelligence is in the eyes of the observer, right? So it is.
Yes, exactly.
It is we see something as intelligent. It totally depends on the viewing angle and the context and everything, right? So it is a illusion basically created in the observer's eyes. So what matters to the animal is, did it survive? Did it accomplish some goal with minimum energy and minimum danger or risk of survival? And did it survive the day? That's it, right? So, and then longevity and things like that. Or did they make enough copies of themselves for the next generation? It can do it in the simplest way possible, and then we may see that as an intelligent behavior. And sometimes we miss to see very intelligent things, and we assign intelligence to the wrong things too, right? Sometimes.
I think it's also interesting with, again, Nikki's talk of this idea of, for example, you needed for a monkey, for a human to be able to, you need to share some of the biomechanic similarity to be able to perhaps, again, label intelligence on the behavior of another. And this idea, as you say, that intelligence is maybe a two-directional thing. It's not just, it's the observer as well as the demonstrator contributes to this perception of intelligence. So I think that's all interesting that you all have very different research topics, but somehow it's all kind of exploring this notion of what is intelligence or what is emergence, and that we all have very different labels for it, maybe. I don't know, Kaspar, you look like you were...
I don't know whether I can answer your question, but maybe it's linked to, my question is linked to it, I suppose. So we always say there's lots of intelligence embodied in the human body. When Thrish and others have, most of you guys have presented fantastic examples, and we always say, so if we create soft robotic hands, then control is, the external control is reduced because these hands are so compliant, adapt to the environment, everything becomes easier. But I wonder why then in the human brain, if we look at the so-called homunculus, the hands take up so much space. I suppose you have heard of the homunculus, this creature that represents our, brain regions, and the hands are the biggest. And that is for motor control, but also for the sensory side of things. So why, if things become so easy, if we make everything softer, is there so much area, space assigned to handle hands?
Yeah, I think also, if I can add to that, so in terms of intelligence, I think the it becomes also complex in relation to human-robot interaction to talk about intelligence, because it is really a coupled system of human and robot acting, but also within a specific environment. So in that case, it's perhaps more appropriate to talk about intelligent interaction. And I mean, there are different kinds of metrics or criteria to use for assessing the quality of that. So it can be in terms of how intuitive the interaction is, or how efficient, or if we are talking about aesthetics, then we also introduce the component of how enjoyable the interaction is. If we are engaging with robots. And I think that it is really a complex to work with. So it is a matter of trying to look at different parts of the system and come up with hypotheses about how they might be connected. But because it also happens within a context, for instance, with human-robot interaction, people's expectations and the criteria for the robot's successful operation. So it's really something that has to be constructed for the specific robot and the specific setting that we are working in, just by gradually changing a few parameters and then doing more trials.
Any other thoughts?
I think to answer Kaspar's question, why hands have a lot of somatosensory allocation, out of all the perceptual systems the human body has, one thing that doesn't seem to age with age is our tactile perception system, right?
Do you mean as a human, so as we go through our lifespan, that the actual performance of our tactile senses don't change, or you mean in terms of just the research question?
System. Yeah, primarily depend on. We believe our tactile perception, like even children, they don't want to believe what they see. They want to touch things, right? So they want to touch and feel things. And then even if you do shopping, like what you see online is something like, yeah, you see it, but like you go real shopping, you touch and feel things. So I think human evolution, I mean, I have this hypothesis that like our hands were the port, the port that connected us to this completely different pathway of evolution. So the ability to make tools, manipulate the environment and then use things in the environment as tools and extend the body. Unlike other animals, they fully rely on their body, but we make things as tools and then we extend our capabilities. So hands needed more resource allocation in terms of perception and control, fine dexterous control. So that is a natural, I think, again, a ghost circuit, right? So how to connect the human body with the environment in the most efficient way to create more ghost circuits. So basically, poise our human body to create more ghost circuits was the hands.
But in a way, it means that, okay, we have very clever tools which already have some intelligence built in, some good features, but then you still need the superpower up here to make them work perfectly, as well as we can today.
I think it is more than the power, the plasticity of the circuits, right? So in the nature, there are things that rapidly change that needs modeling at a high speed, and then there are baseline things that doesn't have to be remodeled very often. So muscles and bones, like cam profiles on the bones, can capture these baseline features in the environment. Muscles can capture, you can train your muscles in like days time frames. And then the synaptic plasticity is microseconds, right? So if you need to model something pretty fast, you need that kind of plasticity. So it is just a mirror of the statistical features in the environment, and then it is reflected in the plasticity in the body. So some circuits are more plastic than the others. So I would categorize it that way.
Is it also related to, maybe coming back to Emily, the use of CPGs for manipulation? Obviously, we don't have these cyclic patterns that we see in locomotion for manipulation. So all of the control that okay, so maybe that's the first question, and that's a naive question is, do we believe, do CPGs play a role in manipulation? And two, does this explain, or does this kind of explain in some ways that we don't have this equivalent kind of offloading from the brain to the central nervous system for manipulation?
The only reason why I sort of tipped my head at that comment is that I don't know. I mean, the plasticity, if we go along that plasticity role and think that a lot of things we do, musicians, for instance, there are very repetitive things, playing the guitar, you know, this sort of stuff, that those manipulations could actually be rhythmical. And then in a plastic setting, are you creating a CPG that controls that trained behavior? You know, like you're training yourself to create CPGs that then make you excellent at whatever that is. And I'm not a neurobiologist, and so I'm speaking out of you know, philosophical thought. But the idea that nerves are so plastic that you could create those patterns, and that's what it is really. You're creating cyclic patterns. Define a CPG. What's a CPG?
Yeah.
I know that it's not a circle with a squiggle on it. It doesn't look like that in real life. You know, so it is interesting when you actually look at the anatomy, when the guys that light up these neurons, it's a mess, right? There's nothing organized about it. It's not centrally contained. It's all over the place. And so I think you could have a pretty fun discussion about what constitutes a CPG. Is it the functional output, or is it the anatomical, you know, amalgamation of neurons? It's a cool idea.
Yes. Or is it kind of related to kind of primitives and this kind of like synergies that we see more like, which we definitely see in manipulation, for example? I guess they're very different. Yeah. I'm just wondering, coming back to growing, I think growing is another interesting thing. And in some ways, Kaspar and Tania, you have your growing kind of robots that are exploring. Are there some underlying primitives, or from a control perspective, that allow us to, again, simplify the control for these, or explore more kind of complex control kind of systems there? What's the evolutionary kind of control pathway? What examples can we look at from evolution that could perhaps inspire the control architectures for these types of robots?
Good questions. I am maybe not enough of a biologist, and also I don't see myself as a control expert. But I would probably approach. So I take inspiration in the widest sense from biology. Growing plants are very different from these everting robots that I presented, I would say. And so I would probably go at it from an engineering point of view and see what kind of control strategies one could develop, to steer these robots while they're going along. So don't know whether evolution could help. Maybe biomechanics and the evolution of biomechanics. I don't know.
Yeah, I think there is some loose inspiration again from biology that could be taken from plants, and I think the way that roots grow as well, and this idea of like circumnutation is my understanding. So I think thinking about how we can kind of use this bio-inspiration and how these plants interact with the environment and use signals from the environment maybe to help with navigation and kind of more automated direction of growth and control might be an interesting direction as well.
Thank you. Thank you very much. So I think we have to wrap up there now. But just before we want to go, I just want to say we've had so many words. We've had ghost circuits, embodied intelligence. Maybe intelligence is not the right word, but are we all talking about the same thing here? Are we? Fundamentally, I think we're maybe all talking about the same thing with different terminologies from different backgrounds. So just as a kind of a quick poll, what are your thoughts? Is this the same thing, the same something that we're all talking about?
Has to be, right? So we are seeing the same thing in different ways. We are feeling it in different ways, right? So depending on the experiments we are doing, it has to be the same thing.
And I also agree. I think we should try to make these robotic structures more clever. So bring the cleverness in there. And bio-inspiration, I think, is useful, gives us a good starting point. But if something else can be found to put more intelligence into the body, that could be also an approach to be pursued.
Yeah, I totally agree. Bio-inspiration is just a source, but it is not a limit.
To the purge either today or tomorrow because Alice is leaving Friday.
Okay, sorry, I think someone's unmuted themselves.
Yeah.
Oh, okay, brilliant, excellent. Fantastic. Well, thank you all so much. I really, really appreciated all your time, fantastic presentations, talks, and also joining this discussion as well. So thank you so much to all our speakers for a fantastic first day. And just to remind everyone that we start again tomorrow at 9:15 BST time, so UK time, and all the talks that we have uploaded, have recorded, will be uploaded soon. So thank you so much again to all the speakers. Thank you. And also now I think we'll open the discussion breakout room. So we have a masterclass with Josh Mongard. Thank you so much, Josh, as well. And then another few sessions of presentations. So thank you very much, everyone. Have a fantastic evening, and we'll see you again tomorrow. Thank you.
Thanks.